for this Zoom seminar. So this is, as I've written this on my notes, and my title is Joint Work with Jason Gaddis from Miami University, Miami of Ohio, not Florida. Okay, so let me start by telling you what the twisted generalized Weyl algebras are that are in my title. So I start with those. I'm going to abbreviate those to TGWA. So this is a family of algebras that includes a lot of different kinds of algebras that are interesting for ring theory, representation theory. And so to define them, we need certain parameters. So we're going to need K is going to be a commutative ring. If you want, you can take a field. In fact, in my mind, it's usually a field. But, and then we need a K algebra, associative unidal. I'm going to call that R. Again, in my mind, usually this is just polynomials, but it does not necessarily need to be commutative, although things are a little easier when it's commutative. And then we are going to take a positive integer n, and we're going to need to take some data from the ring R. So we need sigma is an n tuple of automorphisms of R. And they need to commute with each other. So sigma I, sigma j is sigma j, sigma I. And then T is an n tuple of elements of the center of R. And then, okay, and then I'm also going to need some scalar parameters, mu. So mu ij is a matrix of n by n invertible elements from the base field K or base ring K. Okay, so I need all these things, and I'm gonna put them together to define an algebra. So how do I define the algebra? So what I need to do is that I need to take, okay, so C is going to be an algebra, K algebra, with generators. So it's going to be generated by the ring R. And then I take two n generators. So the two n generators I'm going to denote by x1 plus or minus up to xn plus or minus. And then these generators pass through the ring R by acting with the automorphism sigma. So the relations I have is that xi plus or minus times R is equal to sigma I of R, sigma I to plus or minus 1 of R xi plus minus. Okay, so passing one of these generators through the ring R applies the automorphisms. And then if I multiply one xi, the plus with the minus, I get the ti. Those were the parameters from the center of the ring R. But they don't commute. So if I do it the other way, I get sigma of ti instead. Okay, and then I need to tell you what happens if I take generators with two different indices. So if I take xi plus and xj minus, I can switch them, but then I have to put in that mu, one of those scalars. I pick up one of those scalars if I do that. Okay, so the definition of this with these relations, these generators, gives me an algebra they call C. This is not the algebra I want. So the thing here, if you notice here, is that I've not put any relations between xi plus and xj plus. So in order to get some relations between those, I need to do it sort of in a roundabout way. This is why these are called the twisted generalized Weyl algebras. There are things called generalized Weyl algebras that are a little easier to define. But so for this one, what I need to do is that to define A, and I need to take a portion of this one by a two-sided ideal I. In the two-sided ideal I, there's a couple of different ways to define it. One way is that you take the elements here that are killed by a regular element of R. So it exists in R in R reg, so regular element of R, such that R times C is equal to 0. Okay, so this is very non-intuitive what it means, but the point is that this does give some relations between xi plus and xj plus. Okay, so this gives rels between okay, so this one is the one that I call the TGWA. Okay, so this one is the TGWA. A is my twisted generalized algebra. With, you mean sometimes you can write it like this to say that's the one defined with parameters, mu, r, sigma, and t.
I'm sorry, what is R reg? Did I miss that?
Oh, yes, I said it, but I didn't write it. So those are regular elements of R.
Regular meaning what?
Non-zero divisors.
Can you maybe say why you want to study this? Because it seems rather complicated.
Yes. In fact, so I'll give some examples that will tell you that some of these are actually algebras that we know very well.
Okay.
So examples. So okay, so if we take R to be a polynomial ring in n variables, and we take sigma to be the shift, so sigma I of hj. Okay, I don't have a lot of space there. Let's go to the next line. Sigma I of hj is hj minus the Kronecker delta. And then ti is just hi, and the mu's are all 1. Then the algebra you get is the Weyl algebra, the nth Weyl algebra. So then A is the nth Weyl algebra. Right, so what that means is that the algebra where you can call the generators x1, xn, partial 1, partial n, and the relations are that the xi is commute, the partials commute, and the relation partial j xi minus xi partial j is equal to the Kronecker delta. Yeah, so this is just the nth Weyl algebra of polynomial differential operators on nth affine space. So so this is sort of the example, standard example. But of course, then you can get things that are more complicated, because in general, so in this case, for example, xi and xj actually commute with each other. So do partial I, partial j. You can think of those as being, right, the xi's are the xi plus and the partials are the xi minuses. More in general, that you might have things that are a little more complicated. Also, the sigmas here are pretty simple, just a shift. In some cases, just the identity. The t's are just the hi. Another example that you could get, so I'm going to do an example now where R is just polynomials in one variable, and then sigma is just a shift. So now I only have one. So in this case, I'm doing rank one. So in this example here, n equal one. I mean, of course, you can do the rank one by algebra this way, but I want to do a different one. So now, if instead of taking t to be just h, if I take t to be a quadratic element, so let's say h minus alpha times h minus beta, where alpha and beta are integers, then in this case, and let's take mu's to be still one, just for simplicity. Then in this case, the algebra you get is just the quotient of USL2. It's a primitive quotient.
So what are the generators of SL2 in this picture?
It would be x minus and x plus sort of play the roles of
E and F or whatever.
E and F, exactly, and the H comes from the H in R in the base form. You might have to like rescale some things depending on your convention, but okay. There's other examples. I mean, this, sort of to give you a taste, to me, try to convince you that some algebras that are interested for ring theory, representation theory, can all be considered as examples of these. But more generally, so there's like a pretty large, subfamily of what are called generalized Weyl algebra without a twist. So just generalized Weyl algebras. Which those are usually called just GWA. And those are going to be the case when, in our setting, when sigma I of hj is hj. So sigma I acts as the identity on the other, sorry, of ti. Oh, tj. Okay, so when the sigma is acted trivially on the other ones, for other indices, and when the mu's are also all one, then we get what are called generalized Weyl algebras. And in those cases, as we've seen in the first example, we do have that xi plus and minus will commute with xj plus and minus. So there's already a pretty large family of these GWAs. Twisted generalized Weyl algebras make it even slightly more general. There are some examples of things that are TGWAs, but not GWAs. For example, there's this thing's called multi-parameter quantized Weyl algebras. These are TGWAs, but are not GWAs. I don't know that I really want to write down the definitions for these. I mean, the sigmas are kind of involved for these, but if you look up the name, maybe if you're interested, you can find them. But I mean, so just to maybe give the idea that there are interesting kinds of algebras that arise as the GWAs that do not fit in the sort of other families that have been studied before. Okay, so I'm talking about fixed rings. So we want to look at certain rings of invariance for these TGWAs. right? So the situation is that we're going to have a certain finite group of automorphisms of A, so finite group. And I realize there's maybe already potentially confusion. Now, I'm not talking about automorphisms of the base ring R anymore. Now these are automorphisms of my algebra A that I'm looking at, okay? And I'm interested in knowing what are the fixed elements and what properties does that have? Is it still going to be an algebra of the same kind or not? Okay, so A upper gamma is the things that are fixed by all the elements of this group of automorphisms. And I'm actually mostly interested in the case where this is generated by a single element, phi. So phi is going to be an automorphism of finite order. So yes, I'm actually going to look at a upper phi, things fixed by this automorphism phi. So there are some known results, and people had asked questions about rings of invariants for Weyl algebras before. So there are some known results here. So if A is the nth Weyl algebra, then A upper gamma is not a Weyl algebra. Okay, so there's results here by Smith. I think Smith did maybe the rank 1 case, and then Olive and Polo did the more general case. In fact, there's even more specific results, is that the Weyl algebra is not isomorphic to the fixed ring of anything. So I mean, anything, I should be a little more specific here. So it's not isomorphic to D upper gamma if D is a domain, non-commutative domain, or commutative, D domain and gamma non-trivial. So this is a result of Tikarazzi. There are some non also positive results. So if A is the rank 1 Weyl algebra, okay, and so now we're looking at things fixed by basically things generated by a single automorphism. So A upper phi is not going to be a Weyl algebra, as Smith and Olive and Polo proved, but it is going to be a GWA. It's going to be a generalized Weyl algebra. And that's true for certain kinds of phi. So this is true when phi is diagonal or linear. What I mean by that is that phi of x is alpha x plus beta. So that's linear. Diagonal will be when beta is 0. Okay, so here results were by Jordan and Wells, which proved the diagonal case, and then Gaddis and Wan extended it to the linear case. So there has been some work done on these rings of invariance of Weyl algebras. And so our idea was to maybe try to extend some of these results to the more general family of twisted generalized Weyl algebras. Or at least to ask which of these results, which things can we say in the more general situation. So one thing, for example, that can be observed is that if A is a quantized Weyl algebra, so this was sort of the example that I didn't write down explicitly at the end, but that's the example that is not a GWA, right? So TGWA, but it's not a GWA. Well, it's actually, I mean, it can be checked that A upper phi is not a quantized Weyl algebra again. But there's certainly hope that it can still be a TGWA. So, right, so then the question is sort of what is a good family of algebras that's stable under taking invariance. Yeah, so maybe I write it as a question here. So then the question, if A is a TGWA, is A upper phi also TGWA? Or as in most questions in math, it's more like, okay, well, in which cases is this true, right? What conditions do we need, and all that. So, okay. So first of all, I mean, we cannot answer this question in general. So we're gonna try to focus on some cases in which we can say something. So, okay, so the first thing that I want to focus on is a certain kind of TGWAs that are called K-finitistics. So first I want to tell you what these are. So definition. So A is a TGWA. All right, so then we define Vij to be the span over K. So we apply sigma I a bunch of times to the element Tj. Okay, and we'll look at what that span looks like. If that's a finite dimensional, I guess I said K is a commutative ring, not just a field. So I guess I should say maybe in general, the condition is free of finite rank. But yeah, in my mind, K is usually a field, so I can say dimension in that case. So if that dimension is finite for all Ij, then we say that A is K-finitistic. So if that's the case, then we can look at what is the minimal polynomial of sigma I acting on the space, right? So since these are all the shifts of a certain element, so sigma I acts on the whole space. So we take Pij to be the minimal polynomial of sigma I acting on this. And that's a finite dimensional space, so it's right, this minimal polynomial exists. And then we define a matrix based on the degrees of these polynomials. So the matrix CA has entries aij, where aij is 2 on the diagonal, and it's 1 minus the degree of this minimal polynomial if I is not equal to 2. So, okay, so then CA is a generalized Cartan matrix. So this was work of Putorni and Hartwig. And more generally, this tells us something about the relations in A, right? Because that's the thing that's kind of hard to work with these twisted generalized Weyl algebra, is that the relations are very non-explicit because we take that quotient by that graded ideal I, and so it's often hard to work with these because the relations are not explicit. So this was this is a very useful result, is that xi plus and xj plus satisfy what I'm going to call set of relations so they're not exactly the same set of relations as in enveloping algebras of the algebras, but they're close. So they're like, in spirit, they're very similar to those. And so there's sort of like a little bit of connection there, right? So in the Lie algebra case, you can write those relations starting from the Cartan matrix. So in this case, starting from this matrix, you can also write some similar kind of relations for these TGWAs that lets you work with them a little more explicitly. Although these are not known, so this is again work by Hartwig. These are not known to be a complete set of relations, except in some specific cases. But it gives us something to work with. Sorry, I guess maybe sometimes I should occasionally ask if there's questions, but no, not for now.
I have a question.
There's a question?
Yeah, so what if your cyclic group is like Z mod 2? Can you say anything about what's going on?
Sorry, you have to speak a little louder. I can't hear you very well.
How can you relate a question?
Yeah, what if your cyclic group is like Z mod 2? Can you say anything more about what's going on?
At which point?
So phi is, so you're looking at the cyclic group.
Oh yeah, okay. So yeah, yes. So yeah, I'm looking at automorphisms of find order. Yes. So you're asking what if phi is order 2?
Yeah.
Yeah, that's certainly a valid example that we can think of. Yeah, and I can tell you some examples where we can say something about that. Yeah, there's no issues with that.
So generally speaking, nothing is known if it's Z mod 2.
About the fixed ring A upper phi.
Yes.
Well, that's, I mean, I guess the point is that people haven't really studied these in the context of TGWAs. So this is sort of the first work done in the general concept of TGWAs. So I guess the results that I will be able to tell you will be probably the only results known so far on TGWAs. All the other work had been done before in slightly less generality for GWAs or for Weyl algebras.
I mean, so I guess I'm driving at, if you take like a polynomial algebra, a polynomial ring, then the nice case, of course, is when you have a finite reflection. first thing. Acting on a polynomial, you can say something about this. So is
Right. Okay. Sorry. So you're saying like if I take a polynomial ring and I take a phi of order 2, like a reflection, then the resulting the fixed ring is still a polynomial ring in just in your variable squared or something like that. Is that what you're saying?
yeah. So I mean, is the theory nicer if you work with like finite reflection?
Right. So yeah. So for polynomial rings, like you have results like that. Yeah. So I mean, yeah, I will tell you, we will work with very specific kinds of automorphisms phi in our case as well, because those are the only ones where we can actually say something. So I'll say that in a second. What specific kinds of automorphisms phi we're looking at.
Okay, wait, but so for this question, so if you take phi of order 2, so is it known that if you start with the TGWA, you get again a TGWA? Is this the answer?
Not in general.
Okay, I see.
All right. Okay. So, although actually, okay, so okay, now I'm trying to think if maybe our results simplify somewhat when you're just taking the thing of order 2, and actually maybe if your thing is order 2, maybe it follows from a result. Okay, all right. Let's get back to this after I tell you what conditions I want on phi, and then maybe I can tell you then from that things become a little simpler in the case where we're taking phi to be of order 2. Okay, so let's keep that open. Okay. All right. So so one thing I want to tell you here is that so this condition of being k-finitistic is not very restricted. So the previous examples that I've written down for you are actually all like this. So all previous examples are k-finitistic. And in fact, and all of they're all of type A1 to the n. What I mean by that is that the Cartan matrix is just 2 times the identity. Okay, so all the off diagonals entries in the matrix are 0. So even the example of the quantized Weyl algebra that are not GWAs, but they're still TGWAs of type A1 to the n. In fact, all GWAs are TGWAs of type A1 to the n. Maybe I should write that. But type A1 to the n gives us still a more general family than just GWAs. Okay, but I also have examples that are not of type A1 to the n. Although that's going to be one of the main things that we can actually work with. But so another example of k-finitistic that's not of type A1 to the n. So this is a family that I worked on with Jonas Hartwig. So this is a rank 2 family, but the base ring is still polynomials in one variable, and we take sigma 1 is going to be h minus beta 1, sigma 2 of h is going to be h plus beta 2, where beta 1, beta 2 are two positive integers, relatively prime. We take the mu's to be 1 in this case, also to be simple, make things a little simpler. So one thing I didn't tell you is that there are some conditions on these parameters, sigma and t and mu, that make it so that the resulting algebra is not trivial. Right? So because when you're quotient out by that ideal I, in theory, you could be quotient out by everything and get a trivial algebra as a result. So there's actually some conditions that you can write as equations on the parameters that tell you whether your thing is going to be non-trivial or not. So with Jonas, one thing I did is that we were sort of classifying when these rank 2 things were non-trivial. And so we found this family, and in this case, you can take t to be, you have a wide variety of choices for what your t's can be to make things non-trivial, but it's pretty restricted in terms of what the degrees are. So the degrees of your 2 elements t1 and t2, you're going to have the degree of ti is going to be a multiple of beta I. So the same multiple for both, right? So the degree of t1 is k times beta 1, degree of t2 is k times beta 2. So these are k finitistic, resulting TGWA is k finitistic. And the Cartan matrix in this case is basically whatever you want in rank 2. So it's going to be 2 minus k beta 2 minus k beta 1, 2. So with appropriate choices of beta 1, beta 2, you can get like finite type, affine type, and whatever else rank 2 Cartan matrix you want. Okay, the reason I'm mentioning this example specifically is because one of these will also be one of the cases in which we can say something in terms of fixed rings. Okay. All right. So, okay, I guess one sort of accessory result that we have in this work with Jason is about tensor products. So if A prime are TGWAs, then A tensor over K with A prime is also TGWA. I mean, this is something that was, I guess, expected from before, but no one had really written it down. And same if you add the condition of K finitistic still applies. So if these are K finitistic, this also is K finitistic. And the Cartan matrix for the tensor product is just the block diagonal Cartan matrix with the other two. So this helps a little bit in the sense that we can prove things for certain kinds of TGWAs, but then you can tensor them together to get maybe other kinds of TGWAs to which our results will still apply. Okay, so now let's focus on the fixed rings. So I need some conditions on the automorphism feed that I'm working with. So conditions on feed. Basically is what we call diagonal automorphisms. So what that means is that when phi acts on our generators xi plus minus, it should just rescale them by root of unity. Okay, so alpha is a mi root of unity. I guess maybe I should write that slightly differently. I mean, mi is actually the order of alpha in the multiplicative group, so it's the minimal such exponent. So I guess if phi is of order 2, then all of these should be plus or minus 1, I guess. So that would be a very sort of particular case, sort of to answer the previous question. And then phi should act, if I restrict phi to the base ring R, this should be an automorphism of finite order. Finite order L. And I want all these to be relatively prime. So L, M1, and Mn should be pairwise relatively prime. So this is even a stricter condition. If you're looking at something of order 2, then that would mean that basically phi acts non-trivially only on one of the indices, and it sends that to negative itself, and it fixes everything else. So then in our in the cases that we will work with, that I'm going to tell you in a second, certainly you can say a bunch of stuff. I guess I don't know how hard it is to say things more generally, because the problem sort of comes from those set relations. And so, yes, let me explain that. Right, so, okay, so the question we have sort of, what is this fixed ring? How can we describe it? And we sort of have a candidate of what should be the fixed ring. This is called what's called this algebra B, which is the subalgebra generated by, well, okay, so you need to take the fixed ring of the base ring, and then since these things act as multiplication by root of unity, right? If you take a high enough power, so if you take the correct power of the generator, if you take the generator to the power mi, that's going to be invariant as well, right? Because then that's when the root of unity becomes the identity again. So we can certainly take the subalgebra, and this is a TGWA. Okay, so this is, I mean, this is not that hard to prove. Of the same rank as A. Right, so again, in the case of rank of degree 2 of phi, that would mean that basically you're taking one generator to the power 2, and you're sort of generating everything that way. The question is, in which cases this is actually the same thing as the fixed one, right? So that's sort of the problem. Is that B is certainly included in the fixed ring, but when are they equal? Okay, so because, for example, you could have something like this. And okay, so I mean, the example I thought of is not for order 2. So I don't know if maybe for order 2 things are maybe a little easier. We could say something more in general, but you could have something like this, for example, right? Like you could have an element. So let's say the rank n is 2, and let's say that so alpha 1 is ordered 3 and alpha 2 is ordered 2. So you could have an element like this, for example. Right, x1 plus times x2 plus, x1 plus, x2 plus, x1 plus. And this is fixed because if I act on x1 by 30 order of unity and on x2 by -1, well, then all the scalar laws will cancel out. the problem is that I am not guaranteed to be able to move these past each other to write it just as, you know, something in x1 to the power 3 and something in x2 to the power 2. Right? There's no guarantee that I can move those monomials past each other. So, okay, so what are some cases in which we can prove what we want? Well, type A1 to the n is one of them. So if we have type A1 to the n, so that means that in our parameters that sigma of Tj has to be a multiple of Tj. And that will also imply then that you can basically move xy plus and xj plus past each other. You're just going to pick up some scalars. So in this case, everything works fine, because if you have something that's invariant, you can move them so that you do have just that generator to a certain power. So that's one result. So when as long as R is a domain, so if base ring R is a domain and A is a TGWA type A1 to the n, then so is A upper phi. Okay, so then this applies to then all of the algebras that I mentioned previously that were all of type A1 to the n. And this actually also proves, sort of as a corollary, is that if A is a GWA, then so is A upper phi. This had not been written in this generality before, because people were only looking at like rank 1 Weyl algebras, that those are always GWAs when you take the ring of invariants, but this sort of gives more general statement, and from that point of view as well. So the other case that we can work with a little bit is type A2. Right, so that means we take the Cartan matrix is this one. So that's one special case of those rank 2 family that I studied with Jonas. So in this case, there's going to be some conditions. Again, so let's see, I have a few minutes left. So, okay, so I think I'll just maybe, finish this type A2 and maybe just very briefly mention some other things that could happen. Okay, so if this is the case, then our minimal polynomials will have degree 2, so I can write them this way. And then actually it depends on what these coefficients are. So the result is that, so if certain functions that can be defined recursively, I don't have time to define them right now, but if certain functions are non-zero, when applied to these coefficients, so if that's true for P21, then A upper phi 1 is again TGWA rank 2. And if the same happens to the other ones, then A upper phi 2 as a TGWA of rank 2. But again, now I have to be even more restricted in what phi1 and phi2 are. So phi1 is such that phi1 fixes x1 and only acts on x2. So that says basically that alpha 1 is just 1. And same for phi2. Sorry, acts trivially on the second index generators. So even in type A2 case, we can say something, but it's extremely limited. Certain kinds of type A2, we can say that the fixed ring is still going to be a TGWA, but it's not going to be TGWA type A2 anymore, because then we would have something like this. This new one, it's still going to be part of the same family that we had before, but now this term is not -1 anymore, but it's become basically whatever we want. And same for phi2, you would change the other one. So these are still TGWAs of rank 2, but they're not of type A2 anymore. Okay, and I think I'm out of time, so I'm just gonna say that, so we have some results. Also on ring theoretic properties of these in these specific cases. Like Noetherian properties, Sauring-Gorenstein, Gelfand-Gerlach dimension, Weyl dimension, and we can also say something about restriction of weight modules. So we have, this map, and we can look at restriction of weight modules. So there's a general notion of weight modules for the TGWAs, where sort of the base ring R is sort of acts as your Cartan subalgebra, and sort of the analogy with the Lie algebra case. So we can say something about how simple weight modules behave under restrictions, again in certain types like rank 1 or type A2 and so on. But I think I'm out of time, so I think I should probably stop here. So thank you.
Are there questions for the speaker?
So is there a geometric interpretation of these TGWAs, like maybe in terms of B modules on some algebraic variety, like generalizing maybe some of the things that you see for the Weyl algebra?
Yeah, not that I know of, but it would certainly be interesting to see if there is some sort of more general construction or choosing appropriate things where that gives rise to these. But yeah, I'm not aware of a geometric interpretation for now.
Other questions? Okay, let's thank the speaker again.